Okay, should be live. And our colors today should be much better on the live stream. I'm checking the sound, so hold on. All right, cool. I tweaked the camera a bit, and I shouldn't look as much like a vampire as I normally do. But it was very overexposed in the past. But today I want to talk about a stream that isn't new, but is, I think, important to just start introducing E8 to some of our discussions. And so E8 is a geometric shape, it's a geometric shape that is from higher mathematics and has been now introduced into physics discussions more commonly, particularly when we are discussing theories of everything, because of a man named Garrett Lisi, who is Eric Weinstein's arch nemesis, according to Eric Weinstein. And he came out with this theory to unify physics using E8 that was called an exceptionally simple theory of everything. We're going to take a look at his paper because it's probably one of the best papers I've seen. I just love the structure of it, and the way that it's written is it's just very well done. I'm not going to say that it's correct. I'm just going to say it's well done. And he went on Brian Keating's podcast. I'm a big fan of Brian Keating. He has the Into the Impossible podcast, where he discusses physics and cosmology and UFOs and science in general and all kinds of things. So he had Garrett Lisi on quite a while ago, and I thought it was a great discussion. They talk about string theory, they talk about physics, they talk about physics in general, they talk about beauty in physics, they talk about E8, and it's in general a good discussion. But just to get started, this is the stream that we are going to be discussing tonight. It is Garrett Lisi, an exceptional theory of everything, which is, similar to the name of his paper. An exceptionally simple theory of everything, which is the name of his paper. So that's it. It's on Dr. Brian Keating's YouTube channel. Brian Keating is a professor of physics at UC San Diego, and he's also the host of and creator of the Into the Impossible podcast. So this is Garrett Lisi's original paper. I believe it's his original paper, at least. Oh, man. Here it is. Oh, wait. Here we go. Just taking a minute to load there. But if you would like to support this this podcast, Theory of Every0ne, financially, so that we could get a faster computer, there should be a link to Patreon below. But this is the paper. And it says here, an exceptionally simple theory of everything, abstract, all fields of the standard model and gravity are unified as an E8 principal bundle. Hopefully the stream is still smooth. Bundle connection. A non-compact real form of the E8 Lie algebra has G2 and F4 subalgebras, which break down to strong SU3, electroweak SU2, and U1 gravitational SO3-1. The frame Higgs and 3 generations of fermions related by triality. The interactions and dynamics of these one-form and Grassmann valued parts of an E8 superconnection are described by the curvature and action over a 4-dimensional base manifold. So that's pretty difficult to understand. I understand some of it, but I'm not going to claim that I understand all of it. But I understand enough. And it's interesting that this last sentence are described by the curvature and action over a 4-dimensional base manifold. This is the same thing as geometric unity. It's the same thing as sentient singularity theory with the 4 primary perspectives, which is a 4-dimensional base manifold, essentially. And also Carl Friston's work is has got basically 4 dimensions to it. So, which was, oh man, I've got to look up the exact name of what he calls them. Oh, it's oh my gosh, I'm gonna have to look this up. Hold on, because that's not fair. Carl, I just haven't looked in a bit. Carl Friston. His theory is the free energy principle, which I know, but what does he call it? It's starts with an M. Markov blanket. That's what it is. A Markov blanket. Okay. I didn't find it on here, but I remembered. Okay, so here we go. By the way, please, drop any questions that you have in the chat. Hit the like button. Subscribe if you would like to see more of this. So this is back to Garrett Lisi's paper. This is basically it, just scrolling through quickly. The building blocks of the standard model and gravity are fields over a 4-dimensional base manifold. It's got these matrices, these incredible geometric shapes. Each symbol represents a fundamental or elementary particle. And then you get to see this is E8. The E8 root system with each root assigned to an elementary particle. It's beautiful. The E8 root system rotated a little from F4 towards G2. We're going to see this in a minute, but look at that. It's like a Star of David. And that's a flower of life from Buddhism. E8 root system rotated a little from G2 towards F4, showing E6. It's a great paper. It's just very well organized and concise. But I love that he gave sacred geometry, essentially, which is, things like this from Kabbalah or Judaism or the Eastern traditions in Buddhism, with the flower of life. I love how he gives them their due in his work. I think it's great. Okay, just checking the sound. But a particle explore. Okay, so this is created by Garrett Lisi and these two other guys, and you can see these different elementary particles and also shapes that show different aspects of those particles. So its handedness, spin. You can see the bosons and the fermions. And what's amazing about this is that you can take a look at this and kind of just like spin everything around. It's amazing. That's my dog making groaning noises, so I apologize. But what's amazing about this is it lets you see from all these different angles, different attributes of groupings of the universe, essentially, of different aspects of the universe. So here you have 1, 2, 3, 4, 5, or you could say 4 and a center. Say 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, 7, 8, 9, or 1, 2, 3, 4. You can see that it has this trialic structure, triality, which is why Garrett Lisi took an interest in it, which is this 3, which, if you look, Eric Weinstein says in Geometric Unity that it's not actually 3 generations, it's 2. Well, here's 1 and 2, and then he said the third one is an imposter, which I say the third one is an intrinsic constraint or a constraint. But you can see that this one is different than these two. It's like this is the present and this is the past and the future. And these don't actually exist. This one does in a constant. So, I mean, I'm not saying this doesn't exist. I'm just saying, like, you can see that these are different than this one, just like the past and the future are different than the present because they don't exist. But what's fascinating about this structure is it looks a lot in some instances like this structure, which is the 64 tetrahedron grid that has been created by Nassim Haramein. And if you look at it from just the right angle, okay, well, I guess it's just right there. You can see that it's, if I turn it especially just a bit, it's that. Okay? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, and 4. You can get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's the same. 11, 12, 13. Yeah, it's the same exact shape, though. Having trouble counting a bit because it's all mirrored. Everything I'm looking at a screen and it's like the reflection of what you guys are seeing. So I'm trying to show you, do things according to what you guys are seeing, but it's thrown me off. But you can see that it's basically got 4 on the very sides, 1, 2, 3, 4, and then the center. There we go. There we go. Okay. Has these points that are like 9. So 1, 2, 3, 4, 5, 6 and 7, 8 and 9. It's really hard to do everything when it's all mirrored. But this is the same exact arrangement as this. And as I've stated before, my cosmological verse has 64 gaps in it when it is arranged into either solid, a liquid, or gas. And so basically, my theory is that this is the scaffolding of my cosmological verse, basically, that fills in. It's like everything else that is not the scaffolding. And that is this. Thing right here. But I'm pretty sure that this is also E8 in just a different view. And there's lots of reasons why I think this, but I think that Garrett Lisi's choice of E8 is not incorrect as far as a choice of a geometric structure. But we're going to look more at it here, and then we're going to get into the clips. In mathematics, E8 is any of several closely related exceptional Lie groups, linear algebraic groups, or Lie algebras of dimension 248. Very interesting number there. Same notion is used for the corresponding root lattice, which has rank 8. The designation E8 comes from the Cartan killing classification. I don't know anything about that. E8 algebra is the largest and most complicated of these exceptional cases. I mean, it is beautiful. It really is. And we're going to talk more about beauty in physics later. But as you can see, this is stunning. The structure. You can really zoom in there too and just look at that. Dang. It's just beautiful. And it's considered by many mathematicians to be the most beautiful of shape in mathematics. Interesting. Hess diagram of E8. I don't know if I pronounced that properly, but trying. Looks a lot like Wolfram's work. The quantities in it, though, make a lot of sense with my work. 248, 8, and many more. The structures of it when you start spinning it around in that elementary particle explorer makes a lot of sense. But looks pretty dope. I think Dr. Weinstein was open to the 3 generations of particles on a recent podcast with Dr. Hassenfelder. I don't know if Eric... Well, I don't like calling anybody doctor, but if they're not a doctor, like... And only call them doctor when, like, they're, fixing somebody. But Eric... I mean, I guess Eric does have a PhD, so... Looked like the Ruliad. Okay. A recent podcast with Sabine. I didn't know he went on a recent podcast with Sabine, but I will check it out. But we are going to talk about Sabine because I think it's Sabine. But Sabine said that beauty misleads physicists today, and they talked about it in this stream that they did. But with that, let's get into some of these clips. But hit the like button if you are interested in this content. It helps boost the algorithm and helps more people see it. Okay, so first clip.
It's really fantastic. It's like, wow, there is a magical language underneath our universe, and it's math. And that was just... I started taking my first physics classes and finding out that the mathematics I was learning and kind of developing a facility with actually applied to describe our physical world, much like magic underlies science fiction and fantasy stories quite often. It was really fantastic. It's like, wow, there is a magical language underneath our universe, and it's math. And that was just the moment I was hooked. Ever since then, it was just diving deeper into mathematical physics and how our world works in different ways that are fascinating. And I just kept going with that. And I also have always loved flying stuff. So I actually started out aerospace engineering at UCLA. But I think it was the first career day as in the UCLA aerospace engineering where we went down to an engineering firm and walked out onto the floor of an engineering company and just saw a wall-to-wall cube farm of rotund engineers typing away at computers working on the electronics for drones. And I'm like, yeah, no, I'm out. No way. I want to do that.
I definitely understand that. But the not wanting to work in a cube farm. But so basically, this was an interesting comment that I wanted to talk about because he says that he had this epiphany that math was the language of the universe, and I'm not exactly sure that this is the case. It might be the case. It might not. I think it is. This is going to be a bit of a rougher discussion because on this topic because it's difficult. We don't really know that this is the case or not. But mathematics, according to my work, at least on this subject, is not fundamental. We think that it is, but it's not. It might be fundamental to all the other fields that are currently the fields of our sciences, physics, chemistry, biology, ecology, engineering, technology, whatever. But it's not actually fundamental. And that there's something below mathematics that we used to call metaphysics, but it is it's now being called by Stephen Wolfram meta-mathematics. Get a drink of water. But I think that it's fine whether or not we call it meta-mathematics or metaphysics. We're calling it meta-mathematics because metaphysics has connotations to it now at this point and assumptions. But it's fine whatever you want to call it out of those two. But whatever that is, that's fundamental. And I don't know if that is the language that persists throughout our universe, or if mathematics is the language, and that is the geometric understanding that undergirds the language, if that makes sense. So the CTMU is the theory of everything by Chris Langan, and also very similar to these other theories. Just the focus on it, the philosophical focus is not the same. Lisi is not focused on the nature of the universe, I don't think. It's more like the structure, which is different. And Chris Langan is definitely focused on the nature of the universe. But and he says that the CTMU is a language, essentially. And it would have to be a language and a linguist. So like a dweller and a dwelling. It's like a turtle is usually used when describing the universe, or turtles all the way down, because it's the dweller and the dwelling. It's the shell and the occupant. But you need to have a language and someone to speak the language and to create the language and everything as well. This is why, though, I'm not sure if math is this language that is this fundamental, structure of the universe, or if the fundamental structure of the universe is mathematics, and if mathematics is the language of the universe, or if there is something underneath it and then mathematics emerges. I lean towards mathematics being the language, and it's kind of because it's reduced. Almost, it's like it's not as it's not as fundamental, but it's tough to explain because we don't even have the words for this. So the Donald Hoffman, the creator of conscious agent theory, or the theory of conscious agents, another theory of everything that's similar to Sentient Singularity Theory, my theory, and he said, he references this a lot, that the Tao that is spoken is not the true Tao, which I'm guessing comes from Buddhism or some Eastern tradition, basically, to say, as soon as you speak something into, in a language, you have reduced it. Okay, so it's like, it's almost like consciousness or something like that. It's like, as soon as you speak it, you've reduced it. Or God. This is why you're not supposed to say the name of God in Judeo-Christian traditions, at least, not because if you say it, it's bad, but there is no way to basically convey God in a single word. So the closest it gets is, I am, and whatever you interpret from that statement, which is actually quite a bit. But there's another mathematician physicist named Max Tegmark, and his theory is the mathematical universe, which I think is kind of a cop-out, to be honest, because even though it's not really, it kind of fails, I think. He basically says that the universe is mathematical, and I think that is my dog. I apologize, but that's partially true. But it's not when you're talking about what is fundamental. If you really want to get down to a quote-unquote theory of everything, which I'm not sure exists in the way that we think of it, you have to go into meta-mathematics, as Stephen Wolfram puts it, which is what mathematics emerges from. Language emerges from. Physics emerges from. All of these things emerge from this meta field that is basically the patterns underneath of existence. So if you look at my website, at the very first page, sentientsingularity.com, it says, what is a theory of everything? And it says, a theory of everything is a recognizable, describable, and applicable pattern that occurs in all instances of objective observation and an explanation for such a pattern. Okay? If you look up a theory of everything on Wikipedia, you're not going to get this definition. You're going to get a different definition that is probably, I've looked at it, and most of it is not actually correct for what would be considered a theory of everything, which is basically a theory that unites quantum mechanics and general relativity, which are not even the same field. Quantum mechanics is like where you're starting to bridge metaphysics into physics, but it's closer to metaphysics than it is to physics. The geometric physics of general relativity are more like physics, like thermodynamics and things like that. But I apologize for having some trouble speaking. I built like a misting system for like some geckos and stuff before this, and I was like cutting aluminum and with a power saw and drilling it, and that's got like a little dusty in here and everything like that. And it was quite the feat. I'll share it once it's all set up. I'll share photos or something like that. But turned out well. But aluminum is not fun to work with. It gets everywhere. But I don't know if mathematics really is the language of the universe. But if it is the language of the universe, it's not the fundamental structure of the universe, which is about symmetry patterns, basically. And it's like mathematics is computational, and whatever is the theory of everything, essentially, it's beyond computation. It's just awareness, or through symmetry patterns. I mean, I say awareness because I believe that the universe is a sentient being, but and it's the only way that it really makes sense to have anything below computation, but still even having order to it, I think, at least. I saw the recording you posted on your Instagram story and noticed that the pushback for this latest reprisal in physics is not as severe as it was for heliocentrism or Newton and others. Okay, you shared or you saw my story that was posted by Naval. I think that's how you say his name. And he basically said that scientific advancement is made on the fringes by individuals, and it's not made by groups, and anytime you make something social, you've decreased the truth of it, and you can check it out. It's on my Instagram story. And I very much agree with him, even though I know what he's trying to get at is not something that I would actually try and argue, which is that the social sciences are not really true. They're just because they're just appeals to, the greatest number of people. I would say that about today's proposals in this, what we call, sociology or the social sciences, I don't think that that's actually true. I think Sentient Singularity Theory proposes that there are structures in the social sciences, as you would call them, politics, morality, economics, that would be as concrete as the standard model, because they essentially are the standard model, just projected up into a different field. But like, there's 6 caste systems in Sentient Singularity Theory predicted, and there's a pattern to those that follow every other pattern, including the pattern in the fermions, which would be like the quarks and the electrons and neutrinos. But the electrons and neutrinos, and then the quarks, the up quarks and down quarks, or the masculine quarks and the feminine quarks, as I call them, follow the same exact pattern. It's like a binary triality, which I think is a Calabi-Yau manifold, which we'll get to in a minute. It's this trialic but also binary pattern that is created by a mind interpreting and processing information to categorize it, differentiate it, and organize it into a hierarchy. And but I get what Naval is saying about today's social sciences. They're just a mess. But so is everything. Physics is a mess. We just don't realize it because it's easier to be, to just assume that you don't understand something someone's saying about physics. But as soon as they say it about gender, it's easier to recognize whether or not it's nonsense for most of us, because gender is something that we interact with every day in our world. And I still don't think we get it right on any narrative. It really gets it right, to be honest. But there's certainly some that, like, the abandonment of gender is nonsense. If we're going to talk about our place in the universe and differentiate anything at all. Do you agree, Jason Clarkus? And do I think that the latest reprisal in physics is not as severe as it was for heliocentrism? I don't think that the consequences, looking back, it seems like the consequences were so severe for, those who proposed that, like Galileo, who proposed that, the sun was the center of the solar system. And I think all this is actually, we should be rediscussing this pretty soon after we have this physics renaissance, because the space-time is emergent. So like space and center and all this stuff is different than we think it is. So, but I think the consequences seem like they were worse for people like Galileo back then, because he did face the possibility of death. But, and this is tough, because Sentient Singularity Theory proposes political and moral frameworks and objectivity within those two fields. And I have not gotten too into the deep end with this stuff yet, because I know I'll be banned from YouTube immediately. So, and people will react violently to any kind of objective moral proposals. And it's not the only one, but if you're going to start saying science makes, not science makes, but that through the scientific process, we can test and confirm and propose moral frameworks that are objective, and political frameworks that are objective, and economic frameworks that are objective, this is going to lead to violent reactions. And I don't mean my life will be in danger or anything like that. I hope never. But like, I would be banned immediately to start. And if I were to like hold a rally about sentient singularity theories, moral and political frameworks, it would get out of control. Just because I've been to enough political rallies to know, like, it would be like people shouting, exactly like it is for every other issue right now. And that is a different thing than we've reached yet with this physics renaissance, I guess, that's blossoming. But we will reach that. I mean, it's just impossible not to go down that road. It doesn't matter whose theory it is, really. It's going to lead to that. Because it involves consciousness and sentience, and it's going to involve whether or not the question of whether or not God exists. It's like, is the question of whether or not the universe is sentient, is a sentient being, meaning has feelings, and is self-aware. Is that question more controversial than whether or not the sun is at the center of the, solar system or the Earth? Like, I don't think that we've reached yet where it would be a valid comparison between those two. But we will. And I think that this is where physics is going to be more controversial than whether or not, like, the sun is the center of the solar system or not. But we just have to get there, and we're not there yet. We have to, like, break through this mathematics barrier that is of abstract mathematics into physics, and then from there go to, like, the moral implications. And political implications. What if the way to structure a government is not a question of, like, what is best? It's like, what if there's only one way that is correct, and the rest are just various shades of wrong. That's pretty, like, incredible statement. But I think that my work suggests this, and I think that the work of others will too. So it's a big deal. I believe that's why Professor Wolfram created the Ruliad. It's composed of eames, which are atoms of existence. Yeah, the Ruliad is like it's like from Wolfram's work. I've looked into it a bit. It's like the monad, but it's the monad of rules. I try not to like delve too deeply into everybody's work, because until much more recently, because I finished all my models, but I have started looking a bit more into Wolfram's models, and they're just incredible. His methodology is actually, I think, closer to mine than many others, but that doesn't mean that like exactly how we did, where we ended up is the same. But basically creating smaller structures that are linked together through various rules to greater structures, like not exactly like cellular automata, but kind of. And then his hypergraphs is basically not that different from what my a packing fraction is, what somebody called my my cosmological verse, which is basically connected boxes. They're connected through equations instead of basically his like hypergraph structures, I guess. It's the same type of thing. Science is hope. I don't know if science is hope, but it is interesting. My kid, I do think we're going to be fine, but we're going to go through hell to get there. Kid discovered free energy. I pay the bills. If your kid discovered free energy, that's great. We're going to talk about that later in a bit. Sounds kind of like God. Yes, it does sound like God, because I would argue that it is. Okay, so next clip. We're going to show some of my models as well and how they interact with E8 in a bit.
Back in the 90s, and somehow grew even more from that. So they were right about pointing me that way for the popularity standpoint, but the whole time I'm in Ken's office going, what does this have to do with physical reality? They seem to be talking about a universe we weren't in. And although it was pretty mathematics, and I appreciate pretty mathematics, it just didn't seem to apply to our physical universe. And that's been my beef with string theory. It's just a really fancy toolkit that's really great for doing some things, but there's no indication it applies to our universe. And all the optimism they had for how well it was going to do, none of it panned out. Absolutely nothing. Using higher dimensions, which is an old idea from Klein, that's great, but they couldn't get the standard model out right. They couldn't get anything to work without super partners. So there are all these particles that are supposed to show up, none of them showing up. And it's just, string theory was just a train wreck. And I sort of saw that coming in the 90s, and I'm like, I've got some stock investment money, I'm just going to go do my own thing. And so that's what I did. And it was the most questionable decision I've ever made in my life, but it turned out to be a fantastic one. Just to skip out and do my own thing.
Yeah, having the courage to do that, we'll talk about later. My patented final thrilling three questions I'll ask you.
Okay, so he's talking about string theory, and what is interesting about what he said is something that I agree with, which is that string theory doesn't seem to be easily tied to or tieable to anything in our physical universe. And I have basically realized this through questioning physicists and mathematicians that I've interacted with, basically like, point me to a Calabi-Yau manifold. What is E8? Not E8, but Bott periodicity, which is 8 loop spaces, essentially. So it's like, where's Bott periodicity? I'm not saying that's part of string theory, but it's just like an abstract-ish mathematical structure, and then you've got a Calabi-Yau manifold, which is part of string theory, I'm pretty sure, which is the 6-dimensional manifold, which I believe Ed Witten described as a 6-dimensional manifold at every point in space and time. And then you have, Michio Kaku saying that there's 11 dimensions within string theory, not just 4. And this stuff just goes nowhere. And then somebody's like, well, what are these other 11 dimensions? Somebody's like, well, maybe they're just really, really small. And then there's no evidence of that, and that doesn't make any sense either. And so basically it ends up just not being linked to anything in our physical universe. And it has to be if it's going to be physics. That's the point of physics. It can't just be abstract mathematics. And that's basically where string theory has been failing. But I have an idea as to why this is happening, and I actually don't think string theory is as... I think it has the potential to be reconciled quite a bit, but we have to recognize the context of the structures that we're talking about. And the context of those structures are within a mind, because that is the structure of the universe. Even E8, the context of it is a mind. And it has to be, because that is the nature of reality. And I know people will say, oh, you don't know that. It's like, well, I'm claiming that I do. And, maybe I'm wrong. But, like, I'm going to approach contextualizing these structures into that context. And if you just assume that that's wrong and that you don't know the context of the structures of the universe, then you can't actually attempt to contextualize them into anything, and that means you can't make sense of them. So you have to try it. You have to assume for the sake of argument that it's, something. It doesn't have to be what I think it is, but you have to assume something about the nature of the universe to start contextualizing all of these structures like E8 and the standard model, and like, why did we get the standard model? Why is triality apparent? These types of questions are going to be answered by contextualizing. And so when you look at string theory, and you look at this. Calabi-Yau manifold is a particular type of manifold which has properties such as a Ricci flatness, applications in theoretical physics, particularly superstring theory, form a 6-dimensional Calabi-Yau manifold, which led to the idea of mirror symmetry. So what I think that this is this. So this is what our minds break the world into when we look anywhere. Okay, so you can do this infinitely, essentially. You could find this pattern of 6 infinitely. And it comes from our mind. That's why. And so you can look in the mathematical order of operations, and you can be like, parentheses, exponents, multiplication, division, addition, and subtraction. And so you can see symmetry patterns in these various categories that are created by our mind. And when you contextualize them into the most fundamental context, which would be like my cosmological verse models and things like that, you end up realizing that there is no difference between parentheses, which it means like grouping, and exponentiation, which is like multiplying, but it's not multiplying. It's like growing the quantity obviously in an exponential way, but so it's quantitative growth. Exponentiation is quantitative growth. Parentheses is quantitative grouping. So in order to, just like basically, wow, these are two things that are two sides of one coin. They're not different. You have to group something and think of it as a whole, as like a holonic structure, in order to even think about the growth of quantities, because you have to quantize something. So, like if I do an equation and I'm like, 3, plus 1 or something, and you just like put parentheses around it, now within this greater equation, whatever you're gonna end up doing, this has to be taken as a whole. And what you've done is you've quantized this function, okay? And you need to quantize something in order to have growth, in order to view the growth of a quantity. Then you also need to have the perspective of quantization, okay? Of drawing the lines of where do I end and you begin? Or where does a car end and another car begin? Okay? If space-time is smooth, then why can we look at a car and be like, that's one car, and then we look at a car next to it and be like, that's another car? That's parentheses. And exponents would be like the growth of quantities. And they're the same exact thing, though. Just like multiplication and division are the same exact thing. So in mathematics, they're not. They're different. But in metamathematics or metaphysics, they are the same action. They're just two perspectives of the same action. Same thing with addition and subtraction. So to illustrate this point, think about this in terms of cosmology, where you have a cake, okay? And, you have a cell. And existence, or the universe, is a cell. And it has to create another universe. So how does it do this? In order to multiply itself, it has to divide itself. Just like a cell. A cell divides itself in order to multiply itself. It's the same action. It's just two perspectives of that same action. Addition and subtraction are the same thing, because now think about the universe as a cake, okay? And let's say you have to, or if you're God and you're a cake, and you have to put some cake towards creation, which would be the universe. How do you do that? You have to, in order to add cake to the universe, you have to subtract cake from yourself. So you cut some cake away from yourself and you add it to the universe. And it's the same exact action, but it's just two perspectives of one action. And it's hard to look at both at the same time, just like you can't look at heads and tails of a coin at the same time, but you know both are there. This is the same exact thing, where basically, if you are the universe and God is adding cake to you, then it looks like and all you focus on is cake is being added. But if you are God, then from your perspective, cake is being subtracted from yourself. And or you could say, cake is being added to the universe, obviously, but you're viewing it from a first-person perspective. It's being subtracted from yourself, and from our first-person perspective, it's being added to us. From a third-person perspective, it's being subtracted from God, and we can see it as it's added to us. And from a third-person perspective, God can see it being added to us as he subtracts it from himself. But you can't focus on them at the same time. So you have to pick your perspective. Are you looking at it from a first-person point of view from God? Or are you looking at it from a third-person point of view from God? Or are you looking at it from a first-person point of view from us? Or a third-person point of view from us? Same thing goes with the cell. Are you looking at it as from a third-person point of view of the cell, or a first-person point of view from the original cell, or from the new cell, a first-person point of view, or a third-person point of view? And that will determine whether or not you view it as division or multiplication. If you're the original cell and you are looking at what you're doing to yourself, you're dividing yourself. But if you're looking at what you're doing to another cell, you're multiplying, basically, as you divide. And so if you're that other cell, then you can see that the cell that gave rise to is dividing itself, but you are being multiplied. So it just depends on which perspective you're looking at things from. Or is it first person or is it third person? And are you the creator or are you the creation? And that four-dimensional, those 4 degrees of freedom, okay, of creator and creation and first person and third person, will dictate whether or not you see exponentiation or parentheses, which is groupings, essentially, or multiplication or division or addition and subtraction. And so these different perspectives they're different perspectives, even though they are also like dimensions. But you can see this everywhere. You can see this with your senses. You can see this with with space-time. You can see this with gender and sex and colors and color mixing. So primary and secondary colors. Color mixing. It's like 2 different ways to mix colors: magenta, cyan, and yellow. Green, blue, and red. So additive and subtractive color mixing. So if you look at a screen really closely, you'll see green, blue, and red little pixels. If you are using printer though, and you have to get more ink, you know that you have to get yellow, cyan, and magenta. Somehow those combine to form any other color, and same thing with red, blue, and green. You see this with language, and you see this with rocks, and you see this with questions. Who, what, where, when, why, and how. You've got identity. You've got structure. You've got location. You've got, time. You've got, which is like space and time. You've got reason, why. And then you've got method, which is how. These are also a binary triality, which I think is a Calabi-Yau manifold. It comes from your mind, your limbs, arms and legs, hands and feet, fingers and toes. You can see this with fermions, the leptons, which is electrons and neutrinos. Electron, neutrino, electron, muon, neutrino, muon, tau, neutrino, and tau. Bosons, you can see it with. Fermions, which are the quarks of the fermions. I know I already said fermions, but the quarks, the masculine and feminine quarks is what I would call them. Up and charm and truth, and down and strange and beauty. And you realize through the symmetry patterns in these, what's going on. You can even see this in the theological traditions of the world. I mean, it's just wild. And I know people will be like, you're just seeing patterns, Tyler. Yeah, I'm looking for patterns. That's the point. But you can see there's objectiveness to these patterns. So if you look at your senses and you're like, emotion, taste, and touch are somehow different from sight and smell and hearing. And what is different is that sight and smell and hearing are senses that we use to detect that which we view as separate from us. Okay, so you see something over there, you hear something over there, and you smell something over there. But emotion and taste and touch are how we perceive things that we perceive as connected to us. So, taste, you have to touch your tongue to something. It's like smell, but instead of just smelling it from across the room, you actually have to touch your tongue to something. Instead of hearing something, which is you're detecting, waves of force, okay? You have to physically feel something apply force to you to perceive your sense of touch. And then, or something has to feel connected. And then emotion is also, it's a super literal connectedness, I call it, and we kind of intuitively or intrinsically understand this. That's why we say things like, that painting really touched me. Like if you have an emotional response to a painting or a song or something, you're like, that song really touched me. Or you're like, that I was really moved by that movie. It's like you were moved. You were touched by it. You were moved by it. It's literal. It's not just literally. It's not just metaphorically. It's super literally, which is both and more, connected to you. And that is what manipulates your emotions. So it's like you are being touched, but the emotions are also the sum of all the preceding senses. So what you see, smell, taste, touch, and hear influences how you feel. And the same thing goes with all these other, categories that I have set up here. And I'm not saying all of them are correct. But I've got enough of them here that are, where the other 5 are the sum to, the top one essentially. So your sight, taste, smell, touch, and hearing sum to your emotions. You could say that parentheses, which is like grouped, okay? Everything can be, let's say you have an equation and you're like, you've got multiplication and division and addition and subtraction and exponents in it, and all of a sudden you just put parentheses around it. It's like sum. Everything is sums to that, or I don't want to say sum in this case because it's actually a mathematical equation, but everything is part of that one thing now, and that is the primary is parentheses. It's the first thing that you look at to determine what things are, what aspects of an equation or functions are to be grouped together as one, treated as a single unit, essentially. The same exact type of thing happens with the colors, but it kind of teaches us that there's like more colors than we think, where green might be the summation of all the rest, but not in the context that we think, where you just add a bunch of paints together and of every color and you mix it and it gets like brown. It's like, what is green? The color, at what point is green the color that is the summation of all the other colors? I don't know, but maybe life, like, look at photosynthesis. It's like the summation of all these other processes and colors, essentially. Colors that represent these processes. Blue is water, and yellow and orange is the sun. It's like just look. And I know that seems kind of crazy, but I think that this is much more objective than I'm able to make it out to be right now. We just don't... It's about contextualization into the proper framework. So string theory might be resolved with this type of stuff because it's not the physical universe, but it is the physical universe. It's the structure, it's the framing that we view the physical universe through. That might be where string theory is reconciled, and all these pretty mathematics that appear to be, just abstract, like Bott periodicity, which I think also is it is physical. It is the periodicity of sentience in the universe, essentially, as proposed by me at least. So, but otherwise, what would we even know that? What is that? What is Bott periodicity? What is a loop space? I asked a mathematician once. He had no idea. I asked Eric Weinstein once as well, and he did have an idea, I think, but he said it very vaguely. And he was like, Bott periodicity makes me think of a journey, or a series of journeys, and gives me like religious vibes, is what he said. It's kind of like the Odyssey. And I get what he's getting at, I think, there, but he didn't say anything more than that. He wasn't explicit. But I asked another mathematician, or math PhD, and I was like, what is Bott periodicity? And he was like, couldn't tell me. He was like, it's a series of loop spaces. It's loops of loops within loops or something. And it's like, what is that? That's not... Point to that in the physical universe. And we haven't been able to do that. String theory also has not been able to do this. But these mathematical equations do seem to be objective and beautiful, and so what are they? They're probably mental processes. That's what they probably are. I mean, just a theory. And you can see all these symmetry patterns, and within this Calabi-Yau manifold, or binary triality, you have an increasing of force with the fermions, and you see it, though, also in religions, and that same increasing of force in its proselytization, I guess. You see it in your senses and your limbs, and the I guess the dexterity of your limbs. So you say your limbs are your arms and your hands and your fingers, and your legs and your feet and your toes. And that isn't objective. That's an emergent vision that we see in space-time. You can't believe that that's objective and also believe that space-time is emergent. Shape is emergent, but the way in which we perceive shape might come from these objective manifold structures of where, symmetrical or dimensional symmetries, I guess you could say. It's a good way of putting it, I think. It's like your arms and your hands and your fingers are all limbs of increasing dexterity, I guess, or that allow you to deal with things on an increasing detail. Or if you start from the fingers going up to your arm, it allows you to inflict more force. Okay, it's kind of like in the triality in the standard model, is like increasing a mass, which is an increasing of force. But your limbs divide into these two different categories, where one, your arms and your hands and your fingers are for manipulating your world. Okay? Moving things around you, picking up water. Your feet, or your legs and feet and toes, are for moving you around in the world. Okay? So your hands and your arms and hands and fingers are for animating the world around you. But your legs and feet and toes are for animating you in the world, maneuvering you within the world. If you want to move, you don't use your arms, usually. You use your feet and your legs and your toes. Like, that's the point of them. So a very important way of kind of contextualizing these structures, I think, is that they're going to revolve around goals, and that the future of the theories of everything is that everything is contextualized around goals. So it's goal dependent, it's goal oriented. The universe has a purpose to the things that it does. It doesn't just do. It has reason, it has a goal. And that goal, contextualizing things in that goal, will help you deduce all kinds of things. But I hope that made some sense. It was tough, but these structures are what I mean. It's like the string theory, abstract mathematical structures, and also like Bach periodicity and other things like that. They are the ever-present framing or framework that of our minds. But that's why you won't find them anywhere you look, because they are everywhere you look. It's a forest through the trees problem. You won't ever see a Calabi-Yau manifold because you're always seeing Calabi-Yau manifolds everywhere. And this is exactly what Ed Witten said. He was like, a Calabi-Yau manifold is a six-dimensional manifold at every point in space and time. Every point in space and time. That's the wrong wording probably of it, but it's in every instance of objective observation, you will see a Calabi-Yau manifold. I think. And it says on my website, in the definition of a theory of everything, it's a pattern that is observable and predictable and describable and even applicable in every instance of objective observation, and an explanation for such a pattern. It's not the patterns that are at every point in space and time. They are the patterns that are observed in every instance of objective observation within space-time. It's different, slightly. Like the many worlds interpretation, it has no basis in reality. The many worlds interpretation is, I think the traditional version of it is nonsense. But next clip, because I don't want to make this too much about other things. So, but that was important. Like, that's what I think these string theory structures are. It doesn't describe the universe that we observe. It describes the mind that we observe the universe through.
But that might be obviated, Garrett. On a weekly basis, mailed to my office here in San Diego, and please don't mail me more books because I've got enough to read. But here, I got A Theory of Everything. This is from Norbert Schweitzer. This guy wrote a book. You wrote a paper, but tell me, first of all, Steelman.
Some of these people find me too, Brian.
Well, I always get this funny comment. I'm sure you've gotten it too. Dr. Lisi, Dr. Keating, I get it. Einstein was wrong. I can prove it. And if I do prove it wrong, I will share the Nobel Prize with you. But I'm, not good at math. And I always say, I'm probably worse at math. And I told this to Adam Rees a couple months back, and he said, yeah, how do you think I won the Nobel Prize? He answered those emails, but please don't send those emails. But seriously, this guy's got, it's a lot of math. This guy speaks math. This is Norbert Schweitzer. He's got graphs. He's got waves. He's got, but before we get to alternative theories of everything, a Fermat universe is what this is called. Steelman for me, if you would, string theory. What are the best attributes of string theory? Then I'm going to ask you to strawman E8, and then we're going to go on to update recent developments in your theory, not only of E8, but also in cosmology, as you put it, deforming Lie group. But first, Steelman string theory. What's awesome about string theory?
All right. Well, what's awesome about string theory is all the surprises that came out and strengthened confidence in the theory. I mean, getting quantum anomaly cancellation in the theory was very encouraging, and I think that's what brought Witten on board when he first saw that, and that really got steamrolling in popularity. Also, the idea of just membranes oscillating in higher dimensions, that's a very flexible and rich area to investigate, both mathematically and potentially with the application in physics. So string theory did take advantage of things that had been very successful, like Kaluza-Klein theory, which is this idea of adding extra dimensions to space-time that are compactified into very small shapes, and letting the strings vibrate in those dimensions. You're able to get things that look more like elementary particles as excitations. So it does hold a lot of promise, mostly for the quantum aspects. Also, the avoidance of singularities. So in particle physics, when things are interacting and they come and they interact at points, I mean, anytime you come infinitely close, you get infinitely strong interactions, at least classically. So the idea of spreading things out as membranes, right, where everything's just one membrane inside a larger geometry, allows you to avoid singularities, and that's very appealing. Mm-hmm. So for all those reasons, string theory is very appealing. The problem, of course, is that you seem to be able to build everything with this toolkit except the universe we're actually in.
Because explaining why for listeners who might not be familiar.
Well, it's just not actually very natural to get our standard model fermions out. To get general relativity out is non-trivial, and all these things are just it's kind of awkward to get it, and they were hoping that, like, with the right tweaks, you'd get the masses for the fermions out and the CKM matrix and mixings and everything, but it just it turned out to be extremely convoluted to try to get it. And once you take a theory and you have to tweak it that much to get it to match up to known physics, you lose if you're rational about it, you have to lose confidence in it.
So, so those are some of the pros and cons of it. Before we go on to that, I'm getting some awesome questions from the audience. Let me take one right now. I don't want to get too distracted because I've got so much stuff I want to get to before our mutual friend Eric comes on.
To say space-time can be described as geometry, and derives from space-time.
Okay, this is a good question.
Description going far enough towards a real, then is a geometric description going Ski, who asks you a question. If geometry is derived from spacetime, and if spacetime is emergent, then is a geometric description going far enough towards a real theory of everything? In other words, it's sort of a recursion or regress here.
Right. I would say it's not quite right to say that geometry just derives from space-time, or even that it depends on space-time. I think it's more accurate to say space-time can be described as geometry.
Yeah.
And that ultimately you have to look to mathematical descriptions of geometry, such as differential geometry and Lie groups and representation spaces, and all these mathematical tools, and see how nicely they match up with known physics.
Okay, so what I would say is that space-time is geometric, but it's not geometry. And I wouldn't say that, because they asked if is geometry space-time, and he said no, but space-time is geometry, and I would say space-time is geometric. That's true, but it's not that space-time is geometry. Geometry, I think, exists as just being emergent from interactions of of perspectives, essentially, that we would view as dimensions that then basically, as they interact, they connect, and they form structures outside of even space-time. So kind of like, basically, Irwin, his theory of emergence theory, which is an incredible piece of work as well, and he's kind of connected, I think, to Garrett Lisi. I know that Garrett Lisi has done some things on their YouTube channel. If you haven't watched their Theory of Everything video on the Quantum Gravity Research Foundation's YouTube channel, which is Irwin, I would highly suggest watching it. It's great. But on there, Klee basically is suggesting that the universe is a language, and that it utilizes the interaction of a fundamental pixelization of space-time as a tetrahedron, which is this shape right here. It's a four-sided shape. It's just a three-dimensional triangle, essentially. And that four-sided shape is the base of his theory, essentially. And I'm not even going to say that that's wrong, but if you're going to think about things as being projected into three-dimensional reality, that would be the base three-dimensional shape, is the tetrahedron. It's the first three-dimensional shape that you can get. It's the most efficient. But beyond that reason why he's looking at four-sided shape, and Garrett Lisi is looking at a four-dimensional manifold, and Eric Weinstein is looking at a four-dimensional manifold, and space-time is four-dimensional, and my work starts with four primary perspectives, is because of the basic, much more fundamentally, the four primary perspectives, or Carl Friston's four aspects of a Markov blanket, essentially. So, but the four primary perspectives in Sentient Singularity Theory are what give rise to every other four-dimensional anything. But this is those. For those who don't know what that is, these are the four primary perspectives right here. And it's just inside, outside, separate, and oneness. And they're connected by being defined by each other. Okay, so like inside is separate and oneness. So there's like, now these two are connected and to this one. You could draw two lines almost. Outside is separate from oneness. So you can draw two lines from here to here, but it would probably be that this one you draw two lines from here and to here, but there's a directionality to it. So the information is flowing from here to these two. Outside, the information is flowing probably from here and here to here. And then oneness is the totality of kind of all of these, or it would be like inside and outside of separateness. So it's like, it's just everything grouped together. Separateness is inside or outside of oneness. So it's still defined by oneness and inside and outside, and oneness is defined by outside and inside and separate. So they're all defined by each other. And this is how geometry starts. It's like it's that you can't, as soon as you perceive one of these four primary perspectives, you perceive all of them. Okay? So if you are aware of what is inside, then you are also aware of what is outside, because you can't be aware that something's inside without being aware that it's not outside. And you can't be aware of something is separate from something else if you aren't aware of what would be one with something else. So I am separate from you, but, like, you're aware of that because you know that you're one with yourself, and that's not the same relationship that you have with me. So from one of these, doesn't matter which one, any one of them, you can extrapolate the other three. And so they're basically four sides of one thing, which is a sentient singularity. And that's the beginning of geometry. It's about relationships between perspectives to start. But then, yeah, it becomes more when it's in three-dimensional space. Okay, next clip. I don't want to get too into my stuff alone. I want to actually get through their stream. But the point of this is to relate it to my work. So, sometimes at least. Usually.
We're with a woman by the name of Dr. Sabina Hassan. And scientist in her own right, a good friend, the person you don't want to talk to when you're contemplating career suicide, because she might just push you over the metaphorical ledge. And yet we love her, and she performs a very valuable service, I think. Although I think, and I pointed this out to her in a Twitter battle that we had last week. I don't know if you saw the trolling by Frank Wilczek, past guest on this show, but she put out a tweet that something to the effect that beauty is of no use to physics. And then Frank Wilczek wrote back, "It worked out pretty well for me."
Oh, that's fantastic.
Which I thought was the ultimate troll. But then,
really good.
Then we got into it.
Both Sabina and Frank Wilczek are wonderful people, and I like them both the incredible amount.
Yeah. They say the most wonderful things about you too. But I want to kind of quote from her, in that she put out this tweet or this video about you, Stephen Wolfram, who's been a guest on the show, and Eric in particular. Interesting, she didn't really bring up Max, who we also had a Theory of Everything symposium on the Into the Impossible channel. Please go back and check over the archives. We did that with PBS Spacetime. About 1 million people tuned in over the summer. Nice. But one of the videos that actually prompted me to say, I gotta get my friend Garrett on the Into the Impossible podcast, is this video where she put out, like, I don't have time for your Theory of Everything. And it really was just that. Like, she doesn't look into it. She doesn't think it's useful from the perspective of making progress in physics, and yet she salutes you. She thinks thousands of flowers should bloom. Is she just being, kind to a friend, or is she really saying something of value? Because it seems to me, if she were to take you seriously, it's almost like this, they say the benign bigotry of low expectations. She's saying, like, I'm not even going to look at it, but it's really good that they're doing this. How do you respond to her and her criticism of these beautiful fields that you have just mentioned yourself in your own words just 2 minutes ago?
I think her criticisms are valid and should be weighed highly. I think that without experimental checks, physics can and has gone off the rails into just exploration of beautiful theories that just don't happen to connect to our universe. And at that point, when they no longer connect, even in principle, it's no longer physics. Right? It's just philosophizing about the way a universe could be using mathematics. And I do like her a lot as a friend, and I think if you have a good friend, you can have contrary views with your friends and maintain a good friendship. It's just that her and I views on beauty in mathematical physics are directly opposed. I think beauty is a good guide for physics. I think people have just been using that in the string theory direction and saying things like supersymmetry are beautiful. Even Wilczek holds that view, often much to his financial detriment.
Yes.
But it's just people have different ideas of beauty, and that's valid. And I think in terms of this let 1 million flowers bloom, I also support this idea that people should be exploring different directions and different ideas of what they consider.
Oh, okay. So a few things here. First of all, I didn't fail to mention when Brian Keating was saying that all these people send him these theories of everything earlier, and I mean, I get that as somebody who knows him. Like, I don't think I've sent him exactly my theory, but he's aware of it. And I have sent him like a model, I think, once, and I was like, but it was of Eric's. It was my attempt to understand Eric's theory. It wasn't mine. And I asked him what he thought of it, but he didn't have time to take a look. But I don't think also anybody understood Eric's theory enough to judge whether or not I got it right, other than Eric. So like, really, as time went on, I kind of like realized that. But he said, why don't people send me like experiments for their theories? And he's an experimentalist, and I actually think that's very valid. And I do have an experiment, a couple experiments regarding my work, but we're not there yet as far as like, first I got to publish the paper, which is coming. And then we'll talk about the experiments that could confirm some concepts that are central to my theory. But that said, I do think that it's very valid, though. We need some experiments. And it's, Garrett Lisi said people don't do that because it's a matter of cost. Usually, like, they can afford to like write it down, an idea, but like they can't afford to, test it. I disagree. I think one day I will find the money to do my experiments. I don't know where, but I also don't think I need a particle accelerator to do it. I think a lot of the physics experiments going forward are going to be much smaller scale, actually, and more engineering based and stuff like that, but much cheaper than, the Large Hadron Collider. I don't think we need any more particle accelerators. But I think that the reason why people don't propose experiments is because it's very hard to, first of all, when you're looking for a theory of everything, it's not really possible to falsify it, because whatever you are proposing is the ever-present fundamental pattern or of the universe, or aspect of the universe that you are proposing that as the fundamental aspect of the universe, that is going to be viewable everywhere. So you can't really not see it. It's like it's a forest through the trees problem. It's like you are always looking at the forest, so you can't get rid of it. And it's like if consciousness is fundamental to the universe, you cannot remove consciousness in order to falsify and isolate, things in an experiment, but or that in an experiment. But even Wolfram said this, and he's correct. He said in this, going forward, we're going to want to seek confirmation, not seek falsifiability. And I agree with this. You can test things by seeking confirmation. I've done this in my own work. You say, okay, well, I assume that this would be the case. You look for it, you confirm that it's there, and then you're like, okay, I would also confirm that it would be here. And you go and you look for it over there, and if it's there or not, you can confirm things, but it's not about falsifiability. It's about confirmation. And confirmation is not the same thing as proof either. So to prove this theory or to falsify this theory is not the way to deal with the theory of everything. It's like to confirm an aspect of the theory, which would be like, adding to the likelihood that it would be correct, that the overall theory would be correct. But it's like trying to prove God. You can't prove God. God could prove God. That's it. You can't prove it. I can't prove you exist. You can prove to yourself that you exist, but that's it. But I can't prove that you exist. I can prove that you physically are there, but I don't know if you're just a robot or like an android or something like that. I can't prove you're conscious, but you can prove to yourself that you're conscious. That is the same problem with this theory of everything stuff. It's like you can't prove things as much. You can prove patterns exist, kind of, but it's more by confirming them again and again and again and again. But when you're thinking about things from the perspective of first person, you can't really prove things. It's like to another person, or you can't prove things third person from first person. So if I say, prove to me that the sun will rise tomorrow, that is not something you can do. It's not. But it can be confirmed if you just wait and you say, I believe the sun will rise tomorrow, and then we just wait, and then it does. It's like you just confirmed it, but you were never able to prove it to me. This is the same kind of conundrum with the theories of everything and the patterns that you're looking for. But that said, I do think experiments are going to help with this confirmation process, and they're very important. But they're not very much part of theories of everything being proposed. And I don't think it's just a matter of cost. I think that it is because of the phenomenon I just said, where basically people are still operating in the framework of proof and falsifiability, and instead of confirmation. And so they're looking for somebody asked me once, how do you prove, sentient singularity theory? Or how would you falsify it? And they're like, if you were wrong, how would we know? And I was like, I'm pretty sure if I was wrong, then no one would exist. And I realized that the issue in stating that, because it basically means you cannot prove me wrong. But that's not actually even the way that we're supposed to go about this. The rules change when you're talking about the field of fields, or like the field of all fields, or the field that is fundamental to all fields, like that field, the rules are different than all the other fields, because it's the only one that's not emergent, really. It's like intrinsic. So, but also because I just don't think that a lot of the theories that have been proposed have been contextualized correctly, that have been proposed by serious people. You're thinking about string theory, thinking about loop quantum gravity, and even conscious agent theory, things like this. Like, these are proposed autodidactic universe, CTMU. These are serious proposals, sentient singularity theory, by serious philosophers, serious, mathematicians, whatever. But E8, but it is those usually are not contextualized properly, okay? Because people are trying to avoid consciousness or sentience, or as like the fundamental nature, who are serious, quote unquote, or who are taken seriously. I'll say that the people who are taken seriously are not proposing that the universe is a sentient being, for the most part. There's a few exceptions. That means that you can't properly contextualize things. Like, if you can't properly contextualize string theory, then you can't properly contextualize any of its structures, which means you can't properly make predictions in, like, our universe with it. You can just make mathematical predictions, but you can't make physical predictions, or observable predictions is a better way of putting it. That lack of context is due to the fact that academia in physics and math leans heavily anti-theistic, and that causes an inability to contextualize things properly, which leads to a lack of good experiments, and even being able to be thought of by the people who are working on string theory. They can't even think about it. But because they're not contextualizing things properly. They're not even contextualizing things at all. But for the most part. Also, the other half of the people, it's not even half, it's the majority, of the people who are proposing theories of everything and mailing them to Brian Keating or whatever, like, they are they got a glimpse of the objective reality. I don't want to demean them, because I am one of... my work's more rigorous than most, than the category that I'm talking about here. But at the same time, like, it was a time when it wasn't. And it's kind of it's not my own doing and hard work that I was able to, make more rigorous models. I think that I just had the proper perspective, which I'm not responsible for, that allowed me to describe things more easily than a lot of other people. But a lot of these people, they get a glimpse of objective reality and they're like, I get it. And then they go and they write it up, black hole universe theory, conscious force universe theory, like, they send it to physicists, like, asking for help. And the reason why people believe they have a theory of everything, when they just get, like, they've written like half a page on their theory, and you're like, this is not rigorous. It is because when they got a glimpse of objective reality, they got a glimpse of that ever-present pattern of existence. And remember, a theory of everything is an observable, describable, applicable, predictable pattern that occurs in all instances of objective observation and an explanation for such pattern. So if you get a glimpse of that pattern, you don't have to be able to, like, apply it to every single aspect of the world in order and fit it in with every aspect of the world in order to deliver it, even though that rigor of adding its context in all these different fields does add, to the credence of your idea. But that's why so many people think they got the theory of everything, and don't think they got, like, one idea on physics that they take seriously. Some people will be like, I think time is a flat circle. But that's all they think, and, like, I've had a friend tell me that once, and I get what he's saying, kind of. Actually, I think it's pretty good, but they never took it seriously enough to, like, write to a physicist. And but one day I got, like, a flash of a experiment, and that if it was correct, or if my predictions with this experiment was correct, it would have all these other implications about the universe. And I was like, I went and I told my roommate, I've told this story before, and I was like, dude, you're not going to believe me, and I can't prove it to you, but I just have to tell somebody, I think I might have figured out the theory of everything. And it was like a flash. I mean, granted, there was a lot leading up to this, but I wasn't trying to do it either. I just saw one thing, but it's like a fractal. You don't, in order to see the universe, if it is like a fractal universe, you just have to see one fractal. You don't have to see the fractal that fractal's in, and the fractal that fractal's in, and the fractal that fractal's in, and the fractal that fractal's in, because it's all the same pattern each time. So if you just see the one and you see why, then you're like, I got the theory of everything. So, but they, people will get excited and they write it down. And, there's more to developing these ideas. When you're going to try and actually do an experiment, you have to take that fractal that you saw, and then you have to put it into the context of all these different, aspects of the universe and fields and things like that, in order to reduce it and bring it down to, like, it's into a specific context where you can make a prediction about a physical phenomenon and then measure it and, like, see what happens. And that just takes more work. But before that happens, most people are like, I got the theory of everything, because they got a glimpse of, like, the physical, not physical, the ever-present pattern of the universe. And they're usually, like, right enough to know that they saw what they saw. And I believe them. It's pretty easy for me to tell, like, when there's somebody that actually saw it. But the next issue is, like, describing it and putting it into words is not easy. And that is where things get jumbled, and then they end up looking crazy to a lot of people because they can't really describe it properly. But that doesn't mean they didn't see it. So those are the reasons why I think people don't come up with experiments too much, who come up with these theories. And I will look up that one guy whose book was sent to Brian Keating, because it did look intense. But the thing is whenever somebody writes an entire book on the theory of everything, that's like what's his name? Luis Razzo did that on his theory. It's clear he's got something, but I don't know if you need a book. Like, you don't. I have 4 models that are like the models, and then I have other models that help explain what's going on with those models, but it's like 4 models. That's it. And so I think that the more complicated it becomes, the less likely it is that it's accurate. But that's true of everything. I mean, equals MC squared is very simple, and whatever is even more fundamental than that is going to be even more simple. And I did see Sabine recently released a video of an equation. It was like something equals 0. I didn't see it yet. I will watch it, and maybe we'll review it. But that is probably like 1 is equal to everything, is probably like the equation to the universe, or like 1 is equal to infinity, and or 1 is equal to 0. But it's like 0 is different than an empty set in this context because it's metamathematics. But anyways, but this, when Garrett Lisi's talking now about, in the previous clip, about beauty is the guide. It is the guide. When you look at the quarks, it's like up, down, so masculine, feminine, charm, masculine, strange, feminine, truth, masculine, beauty, feminine. Truth and beauty are 2 sides of one coin. You can't focus on both of those attributes at the same time. But what is true is beautiful. And this is a concept in theology. They're like the good, the true, and the beautiful. What is good, is true, and is beautiful. That's accurate. It's always accurate. There's no such thing as beauty outside truth. And I've talked about this before, and it's like, what is beauty? And so you have Garrett Lisi saying that physicists and people are disagreeing about what is beautiful. And Eric Weinstein talked about this on Joe Rogan, as like, what is a good guitarist? What is a good song? On last time he went on there, when he was talking about his theories, like, he's trying to talk about objectivity. And basically, I will say, like, it was not the best interview, and also Joe Rogan wasn't helping. He was like playing devil's advocate, and he was like, lots of people don't like, rock, so like, not that guy's work isn't beautiful. It's like, it's good, like, what talent is, and like, don't just play devil's advocate for the sake of it. But there is objective talent. Which is when something beautiful is expressed. And I said on here before, how do you tell if something's beautiful? Basically, it means it's like always beautiful. So you can tell this about like clothing is beautiful if you like imagine somebody wearing that piece of clothing as a child, as an adult, and as an elderly person, like a young adult and then as an elderly person. Same outfit. If it doesn't look weird on any of these ages, and it doesn't look weird in different contexts either of like location, so like imagine wearing it at the beach and in the office and at home. If you can wear something at home, at the beach, and in the office, and you can wear it as an 80-year-old, and as an 18-year-old, and as an 8-year-old, and it always looks good and doesn't look unnatural or weird or awkward, that's something beautiful. if it's something that only looks good on an 18-year-old at the beach, but doesn't look good on, an 80-year-old in the office, like a bikini on an 80-year-old in the office doesn't look good. Like, you'd be like, what the heck? That means that it's sexy. It's like, it's got something about it that is kind of not beautiful, but it can contribute, or it's like building on beauty, but it's not actually beautiful. Same thing with like songs. So if you see an 8-year-old listening to Lose Yourself by Eminem or something, it's weird. If you see an 80-year-old rapping Lose Yourself by Eminem, it's weird. If you listened to it and you played it at the office, it's weird. But if you play it at a party and you're 18, then it's fine. That means that song, it's a sexy song. It's not a beautiful song. Whereas there are songs that you could listen to at the beach or at the office or at home, either 80 or 8 or 18, and like those songs that you could always listen to, like maybe even like Don't Stop Believin' by Journey. Like, that song fits everywhere. Beautiful song. That doesn't mean you might not you like it. You might not like that song, but it's beautiful. We need to figure out how to do this with physics and math. It's like, how do we test what math is truly beautiful and what math is sexy? And I think a lot of math that people think is beautiful is actually sexy, and it's not really beautiful. And I don't know how to do this with math. I need to think more about it. But okay, this is the abstract of Lisi's latest description of the universe.
Frank Wilczek did with Sabina last week, but for example, the title, and normally I don't have time to read the entirety of an abstract in a live stream like this, but the paper that you published about about E8 Lie group cosmology, rather,
yeah.
The abstract is as follows: Our universe is a deforming Lie group. Come on, Garrett, you knew that would set people off. Although I don't disagree with some of the first statements that you make. To the best of our current knowledge, this is in the text, not the abstract. The abstract is shorter almost than the title. That's very rare. Although I have seen some abstracts where it asks a question in the title and then the abstract is no. So. But the best of our knowledge, the universe exists as quantized excitations of a fiber bundle. Explain what you mean by that.
Okay. Our current description of quantum field theory, coupled with general relativity, as we understand it, is to imagine spacetime as a four-dimensional manifold with Lie groups attached at every spacetime point. And then also representation spaces of those Lie groups attached at every spacetime point. And that this whole structure together is a fiber bundle, and that elementary particles are quantum excitations of this fiber bundle.
Bingo! I agree with him. That's correct. So, what is a fiber bundle? Let's look at this one. This is a Hopf vibration. And it's a fiber bundle. Okay? And so this is an animated object. It's moving. It's not just like static like this. And when he's saying the elementary particles exist as quantized excitations of a fiber bundle. That I agree with 100%. And what this is it's a mind. It's like a geometric, mathematical, three-dimensional representation of a mind. Well, it's actually a two-dimensional representation of a three-dimensional shape. Kind of three-dimensional, but at least it's trying to be... What it looks like is three-dimensional, but it's obviously two-dimensional. But then they'll say it's not even three-dimensional, it's more. But it's four-dimensional. So what quantized excitations of a fiber bundle are is when these... Imagine you are this. If the universe is a bunch of minds within minds, and this is one mind, and then inside it is this mind, and inside is this mind. So this would be the universe. This could be you. This is just an example. This is a cell inside of you, and then maybe that's an atom or something. When the strings of information, which are these strings, cross, okay? Essentially. So when a string of information from this fiber bundle, your cell, crosses with the string of information from your fiber bundle of your mind, which is, this, let's just say, you get an excitation, and that manifests in a quantized observation. So like you see it as like a point. So like when you cross two strings, you'll see a point in which they cross. That point is an elementary particle according to Garrett Lisi, and I think he's correct. And which elementary particles they are depends on which strings cross. So like my theory, at least right now, states that that electrons and neutrinos, the difference between an electron and a neutrino is basically whether or not, gosh, this is tough. It's like, it has to do with movement. So an electron is moving, it's showing a wave that's moving. And so when two waves, which is two strings, intersect, you also get like a particle in that moment, and that's an excitation of a fiber bundle as well. It's just like you can think about it as two waves intersecting. When those two waves intersect, you'll see a quantized, perspective, which would be like a point in which those two waves intersect, and then you'll get it like an electron. So basically, an electron is, either it's basically where the waves of it's the waves coming from an atom, or like a nucleus of an atom, or nucleon, or which would be like a hadron, are intersecting with the waves from the universe, essentially. So imagine there's waves in the ocean, and then you throw a rock into the ocean or into a lake, and there's waves in the lake, and you throw a rock into the lake, and now all of a sudden there's ripples coming out from that rock, but that you threw into the ocean, which would be like a proton or a neutron or something. And then that wave that comes out from them, you could say that's an electron. But then it becomes quantized when you see that wave intersecting with the wave of the medium that it's within, or the wave that it's within, the greater wave, which would be like the wave of the lake or ocean. So it's probably a terrible way of describing it, but when waves cross, you get particles. When strings intersect, you get particles, because you get the ability to perceive a quantization, essentially. And I realize this is not the way that they would word it, but you're a mind, and you have strings of information being processed. When those strings of information cross with the strings of information that are being processed by either you, other strings of information, and just one string from you and another string from you is intersecting, those two strings are intersecting, or your strings of information are intersecting with the strings of information of I guess you could say, lower minds, so like cells within an organism. Those intersections can also manifest into like a quantized point. Okay, so that's what the elementary particles are, and whether or not it's a neutrino, or whether or not it's an electron, or whether or not it's even a muon or tau, or whether or not it's an up quark or a down quark, these are dependent upon which strings of information is going on. So my theory basically states that up quarks and down quarks are literally like the fingers of God, or the fingers of the universe, and that's why they're never found separately from each other. And like a proton would be like a dominant hand. It's like right hand if you're right-handed, and so you've got two up quarks, so two fingers, and then one down quark, which would be a thumb. So two fingers and a thumb, and then you have the feminine quark, which would be, or the feminine, which would be a neutron. The feminine hadron, which would be a neutron, which would have two down quarks and an up quark, which would be two fingers and a thumb. And this allows you to like manipulate things in three-dimensional space. So is to have like two fingers and a thumb. Try doing things with just one finger and one thumb, or two fingers and no thumb, or like just a thumb. It's like you can't do it. So you need two fingers and a thumb to really have all the degrees of freedom necessary to have freedom of movement in three-dimensional space. So, but those are also fibers in a fiber bundle, and you can contextualize them in the framework that I was stating, because you put them into a goal, into the framework of a goal, and thing, behind the being animated by sentience and things like that. So it changes the context. But then electrons would be different, and then neutrinos would be different. Maybe neutrino is when a wave of information, or a string in a fiber bundle, hits another string that's not in motion currently, or it's not even like a wave. It's like it's hit like kind of a frozen wave. And this is just in like a speculation, but basically it's not animated. It doesn't have movement. Whereas an electron would be like two animated waves hitting each other, and then you'd see like a charged quantized point appear. And this is also why electrons, though, are like, when you observe an electron, it has to do with probability. And probability doesn't really exist objectively. It's just geometry, but like contextualized within like a sentient observer who's separate. So like geometry sets the constraints and degrees of freedom of what is possible for you to see, and what the likelihood of you to see a point in that particular location. So maybe you're like 33% likely to see an electron in that point. That's because of the geometric structure that is really what that electron is, that you don't see in its totality. You just see a quantized point. But your interaction with it, and its interaction with you, because it's all coming from sentience, is what gives rise to the perception of probability. It's like emergent. but it's not fundamental. Fundamentally, probability doesn't exist. It's just determinism and choice. So like, I choose to do this, and therefore this will happen. There's no, it's not probabilistic. It's like 100% depending, but it's also dependent upon choice. And the interaction between two choosers is what gives rise to probabilistic perspectives. But it is, anytime we see these like fundamental particles in the standard model, which is like up quarks and down quarks and neutrinos and electrons, and they come from interactions between strings of information, which is that is what a quantized excitation of a fiber bundle is. It's like the crossing of the strings. It's like Ghostbusters, don't cross the strings, or whatever they say. But it's like that is what's happening. I'm really struggling at speaking about this, but hopefully you guys get it a little bit. When you cross two strings, they cross at one point. That point is an elementary particle. It is us observing a quantized observation. It's information in context. In context of what? In context of each other. Like the different strings crossing that into that single point are contextualizing of each other, and therefore give rise to whatever particle that you see. Depending on which strings get crossed will determine which particle it is. So it's tough though to think about this because it's unlike anything else that we think about, but it's also like super simple once you get it. But it doesn't mean it's super simple to describe. It just means you can visualize two strings crossing in that fiber bundle structure, and that is a particle. I like to think of the core zero as the root from which our tree grows. I don't know, periodicity like a circle. Adding or subtracting, it's drawing. It's not adding or subtracting, it's drawing imaginary borders. Yeah, it is drawing imaginary borders. Sometimes they're imaginary, sometimes they're not imaginary. You and me are not imaginary. Like, the difference between you and me is not imaginary. To us. It's real. Maybe to God it's imaginary, but not to us. I don't know what you mean by core zero. Everything starts with one. Periodicity, like a circle. I don't know. Is that like a period and then a circle is like a period? I would agree with that, if that's what you mean. But a periodicity is like when things come full circle, that's a period. So you can get periodicity, though, is like a circle within a circle, which is like loop spaces. Loops within loops, or loops of loops within loops. It's like periodicity. But if you look at a hop vibration, it is loops of loops within loops as well. And it's information processing or it's information contextualizing around itself, and also creating a periodicity, 1, 2, 3, 4, in itself. And when these strings cross, you get an excitation. We're going to have to do this again. Like rotation. Yeah, like rotation. When you look at my website, you see this periodicity manifesting in my model here. You can see that it's like it rotates. After it goes all the way across, it rotates one, and then it goes again, and then it rotates, and then it goes again, and then it rotates, and then it goes again. And each one of these is connected to each other. And this is obviously just work in progress, so I know it looks messy, but here, every single one of these is connected, just so anybody that doesn't realize. If you put this as 0, everything changes to 0. And if you put this as 1, everything changes to 1. And it's like, and there are 720 little squares in this. But you could use this probably to determine the, like, somehow through this you would see the mass and stuff like that for the elementary particles come out. But their charge and spin comes out of this model already. All right, 2 more clips and then we're going to go. This is whether Garrett Lisi on why we, or whether or not we need a quantum theory of gravity.
This is the. It normally goes like this. We need a quantum theory of gravity because we don't understand gravity in very strong, or the quantum nature of gravity in very strong gravitational fields, such as at the singularity of a black hole, or at the beginning of the universe, if indeed the universe emerged from a Big Bang scenario. So then I've always point out, well, both of those things are forbidden from experimental evidence via the so-called boundary or Hawking or the event horizon in the case of a black hole, and the boundary conditions of the initial singularity are also firewalled off from us. And I had this conversation with John Preskill last week. In general, that physicists should adhere to what Feynman said, which is that I don't care if your theory is beautiful. I don't care how logical it may seem to you. If it disagrees with experiment, it's wrong. And I said, John, what if? And he's the Feynman professor of physics and a good friend and influence. And he said, well, what do you do? I said, what do you do if you can't experimentally test it? And he really said, try harder. And I respect him, but the point that I'm trying to make is, what if God hands you an email, and it sends you an email like that movie God Friended Me, which, or the TV show God Friended Me. I'm a religious watcher of it, no pun intended. But the point is, what if you find out there is no singularity at the beginning of time? Roger Penrose is right. There's a conformal cyclic cosmology. There's no initial singularity. And 2, that the black holes never exist in naked singularity. So you'll never witness it. Therefore, I would say, do we need quantum gravity? What do you say?
I would say that we don't need quantum gravity in a practical sense. However, and I agree with you in that the universe did not necessarily start at some moment in time. It could be eternal. Mm-hmm. And in fact, if you sort of follow the argument in this Lie group cosmology paper, that sort of speaks to an eternal cosmology where something was just expanding eternally from back in negative infinity. Mm-hmm. But in terms of whether there needs to be a theory of everything, there doesn't need to be one, but it seems compelling that as we learn more and more physics, as we've learned more about the existence of more and more particles, that it seems to have fleshed out a more complete looking set. So as we discovered more fermions, it fleshed out 3 complete generations and no more. And we seem to have and now it's getting harder and harder to find new particles. And we strongly suspect that dark matter is at least one, if not a bunch of new particles of some sort. But still, it looks like the picture that we have is getting more and more complete, but it's still kind of a mess.
Mm-hmm. And yeah, go on.
And for gravity itself, as you say, we don't have experimental access to the interior of black holes. So we might never be able to have access and experiment to such strong gravitational fields, but we could still potentially see quantum gravitational effects even in weaker gravitational fields. Mm-hmm. Mm-hmm. And there are, you can argue that if you just have to apply quantum mechanics to existing theories of gravity in some naive way, gravity has to have some quantum description in order to be consistent with the rest of quantum mechanics.
Yep.
Right. So just for consistency, there has to be some something going on in the universe with quantum mechanics and gravity, just for consistency. And we don't have a consistent theory of quantum gravity. So that's why there's motivation to look at it, even if we don't have experimental access to strong gravitational fields down at those tiny scales.
So yeah, that's true. I think essentially, but I mean, the graviton problem is a forest through the trees problem. We're looking for something small, and it's not something small. It's something you're inside the graviton. I think, at least, and to understand it more and its interaction with the other particles, essentially, or its relationship with the other particles, like the Higgs or something, you're gonna have to understand its context, which gravity is. It's sentient. It's sentient action. So, like, if I move my arm to pick up this glass, like, my cells now have all of this force that they have to deal with that is moving them no matter what it's moving them. And they can overcome that, actually. They can move from a different part of my arm to a different part of my arm, like it's a blood cell or something. And but no matter what, like, the arm is moving. So if they stay in the arm, they can't overcome it. They'd have to, like, but they can move against it. This is very similar to, like, gravity. It's like gravity moves space. If I move my arm, I move the space of these cells. Like, I'm moving their space. They can also maneuver inside this space. Okay? They can overcome it. Just like you can jump and overcome gravity, but really you can't overcome gravity by jumping. Because you go back down. But that's because your space is being moved, and it's being moved faster than you are being moved. So, or than you can move. So no matter what, if you try, it's like trying to swim upstream as a fish. If you aren't able to swim faster upstream than the stream is flowing, then you will always move in one direction. Same thing with time, and space-time is one object. It's just a perspective of a single object, which is the graviton, I believe. And so they're trying to quantize gravity, and I've always at least interpreted this to mean, like, they're looking for a little tiny, boson, that subatomic particle that is the force carrier of gravity. And it's like, I don't think that they're going to find that. At least not in the way that they think. And if they want to contextualize it properly, they're going to have to think about it in terms of sentience. And but you can make gravity for your cells by moving your arm. Like, you just gave your cells essentially gravity. And I understand, yeah, they have gravity, like gravity. But I mean, like, that's kind of also essentially would be interpreted by them as gravity, I believe. It's like their space is moving. Okay? Like, it's not just like a force that's being inflicted on them. Like, their space is moving. And I'm talking about this on, like, a mathematical or metaphysical level, where on the mental level of a cell being a mind, be within you as a mind. And so, just for kicks, if you wanted, be like, gravity, electromagnetic. I don't know if this is, like, if they're going into the correct squares here. But I'm just, for the sake of Okay, you'd be like, this would be like and this would be like maybe the strong force would be the gluon, and then the weak force would be maybe like the WC, and then this would be the photon. So like they're looking for graviton as like being similar to a photon or gluon or W particle or something. But I would think that it would actually be like these are three perspectives of this. So kind of like could be like space. Just be like length, width, height. Or like time and past. And or this would be like past. This would be like present. This would be like the future. It's like these are three perspectives of this. The same thing is going to be true of this. These are three perspectives of this. We don't see that yet, but that's my prediction. So I think that trying to find like a little graviton, like next to a boson, like a Higgs or something like that. I'm just throwing things out there. Like you're not going to find a graviton like a photon. That doesn't mean proper contextualization wouldn't allow for the manipulation of the force that we would interpret as gravity or something. But like, they used to call, I think, it gravity A and gravity B instead of strong force and gravity. And so, what if it's like strong force is gravity, in like if like we wanted to manipulate gravity and do like anti-gravity, you would actually want to be focused on the strong force and the electromagnetic force and not be looking for a little graviton. You'd want to focus on photons and gluons. I bet that's probably more accurate, but that's just my thoughts on the matter. I'm still thinking of an experiment for that, but I'm sure that it's possible to experiment with that idea. But as for the final clip, this is Garrett Lisi's life advice, and I thought it was good because I was trying to end on like a positive thing. Everybody that I always have on these streams, essentially, or any of these streams that I include on here that I give my commentary on, that means that I think that those people and those conversations are valuable to this discussion. So I am not here to like rip anyone down. I recommend subscribing to Brian Keating's YouTube channel, Into the Impossible. It's linked below. I recommend looking at Garrett Lisi's Elementary Particle Explorer, checking out his Pacific Science Institute, and reading his papers and checking out his TED Talk, which I also linked below. And I think his work is very valuable. I have my disagreements with everybody, but big fan of everybody who I discuss on these streams always.
A little way past them, into the impossible. I want to ask you, and that's the name of the podcast. Garrett, what seemed impossible to a 20-year-old, a 30-year-old Garrett Lisi, that because of your courage and your indomitable spirit, you accomplished it and went a little bit into the impossible?
You have to try things that seem outlandish. And make the choices that are really, you see, making you happy long term. Even when they seem unlikely. But also hedge.
And someone's asking me about Bitcoin in the last 10.
I love that. That was so funny. I was a finance major in school, so that was just funny to me. But it's like, pursue your dreams, but also hedge. I live in LA, and I lived near where, when I first moved here, where a bunch of actors and stuff and singers and writers live, and I lived with actors and writers when I first moved here, and also rappers and all kinds of stuff, and some of them have had incredible success, actually, like as writers, and some of them have had decent success as actors, and some of them have had okay-ish success as writers or actors, and or rappers or whatever, and everybody was talented, but they were all here pursuing their dreams, and I was the only one here for business. I was like, wanted to work at Google when I first moved out here, and I was working for a company where a bunch of people went and would work for Google afterwards, and they were just like, there were just watching them pursue their dreams. You should pursue your dreams, but I just remember watching them and thinking, like, basically exactly what Garrett Lisi said. Is like, pursue your dreams, but also hedge. It's like, you can always pursue your dreams. It doesn't mean that you have to make it your job. We can't all get as blessed as Garrett Lisi. He, for those who don't know, he invested in Apple in like the early 90s. And he invested in some kind of fruit company, and then now he doesn't have to do anything but windsurf on in Hawaii, and physics, which is good for him. I'm not complaining at all. That's awesome. But I would imagine that he didn't expect that to work out as well as it did. So I would imagine that he had hedged, but I think it's good advice that he gave. It's like, pursue your dreams, also hedge. And he did say something important. It's like, do what you think will make you happiest long term. That is really important. Happiness short term and happiness long term. They are two. It's like, happiness short term is pleasure. Happiness long term is fulfillment. And he was like, pursue what will make you happy long term. So pursue what will make you feel fulfilled, essentially. And I think that's great advice. Any final questions before I get off? I think that was, it's a great stream that they did. After this, they did a stream with Eric Weinstein. He gets on, and they talk more about the theory of everything. I love Garrett Lisi's talk with Eric on the portal. I have spoken about it before. I'll probably also do an episode about it again in the future, now that we've introduced E8 and everything. This was a bit of a choppy stream, but their conversation, and this is nothing against them, was much more casual. So it's hard to like do a commentary that's so concise on a stream that was also not the most concise, but it was a great conversation. That's not me ripping on it, but like his discussion with Eric on the portal is like a next level discussion. I think I've listened to that discussion more than I've listened to any other podcast in the world. I don't know what it was about it, but I just like, it was, if you watch that discussion, you can read between what they are saying. They are saying things between the lines of words that they are actually speaking. And about the nature of the universe. That is not happening in like any other discussion I've seen with Garrett. But there's points where they're like discussing the nature of the universe, and they're discussing beauty and why do things actually appear to be beautiful, and is that just random, and why, basically the why, which is not, people say science doesn't answer why. Theory of everything has to answer why, and not just why, but who. And these are the two questions that are not answered by our current subjective fields: is who, why. But if you want to understand where the universe came from, you need to understand who made it and why. That's the context of where the universe came from. So you almost like could say, where came from, where is the intersection between why and who? It's when we're looking at that binary triality of like who, what, where, when, why, and how. But yeah, it's fascinating. I interpret their discussion as basically saying the universe makes choices. And I think they say it a couple times, but they kind of like act like they're saying it metaphorically, but they're not. I don't think so. Anyways, any final questions? Please hit the like button. It helps boost the algorithm. I know it's like it's not actually natural to hit the like button on a YouTube stream like it is on like Instagram or something, but it does help. And please subscribe if you like this discussion. We do this every Tuesday at 7, between 7 and 7:30. Working on getting that more consistent, but it's every Tuesday between 7 and 7:30. It is that consistent. And then we have the Discord community where we have a live call every Thursday at 7 p.m. Pacific time, and it's just open, discuss whatever you want. It's a really good group of people, and you can ask me any questions. And like I said, it's live voice call. It starts at 7, it goes till midnight, and it's always a lively discussion and a good group of people. So if you would like to join that Discord community, then send me a private message on Instagram, either Theory of Everyone's Instagram or Tyler Goldstein's Instagram, or even Sentient Singularity. There's also that Instagram, which is kind of a backup to Theory of Everyone. You could send me a private message on any of those, and I will send you the link to the Discord. And you can join our call, or just lurk. And we have a bunch of different channels on different topics and things like that. But paper is coming soon, and very soon. And we're also going to do some merch after the paper comes out. I don't expect it to replace my income, but there's some cool ideas that I came up with. So we will see, how well those do, and but we'll just pay attention to the website, and there's definitely a lot of changes that have been happening to it. But right after the paper drops, which will be on the website, I'll keep the most up-to-date version on there for people to download. There will also be a shop. So I don't ever post the link to the Discord anywhere. You have to ask me for it. It keeps the community real. We just get you get a bunch of trolls if it gets too easy to get into Discord or something. But it doesn't look like there's any final questions. But with that, I will either speak to you on Thursday, or I will be back next week. But thank you to everybody that stuck it out, and especially thank you to Garrett Lisi and Brian Keating for the discussion that they had. It is a good one. I recommend listening to it all. like I said, linked below. And, yep, that's it. Peace.